Hi, I'm Zor. Welcome to Unizor Education. I would like to talk about different kind of integrals, different from whatever we were using before. So let me just remind you what was before with regular definite integrals. You have a function and we defined it on some interval from a to b, and this is the graph of the function, for example, and we needed to calculate basically the area under this graph. So we divided it into small pieces, assumed that within this piece the value of the function is basically the same thing, and the area was a rectangle. We multiplied if this is delta xi, this little segment, a small one, and the value of the function was, let's say on the left side of this interval was f at xi, and delta xi was actually xi minus fun. So then we have to multiply by delta xi, that's the area of this little thing, then summarize it, and then have the limit when all the delta xi goes to 0 and the number of intervals goes to infinity. So that's basically the definition of this integral of a regular function and regular real interval. Now what I would like to do is to introduce an integral of functions defined not on a straight interval from a to b, but on some kind of a curve in space. Well, obviously if it's a curve it cannot be one-dimensional, so it's at least, you need at least two dimensions to have a real curve. So I will explain it on 2 or 3, maybe 3 dimensions would be even better, and the curve is a curve in space. Now, if it's a two-dimensional curve, and I can really put it on the plane, and then I will have a z-coordinate, so this is xy plane, and on the z-coordinate I have value of the functions, and value of the functions go along some curve. We also can really consider the area of, it's basically a cylindrical surface, and we can also calculate the area exactly the same way. Divide this little curve into small pieces and put each area would be not exactly a rectangle but a little bit curved rectangle, because this line is a curved line, not a straight line. But still, when these little intervals, which we can call delta s, let's say, are really small, we can consider it as almost a rectangle. And obviously, if the curve is smooth enough and the function is smooth enough, we can actually when the number of these intervals go to infinity and each one of them is infinitesimally small, then we can consider it in exactly the same fashion as we did with regular integrals. We just multiply the value of the function of si times the length of this little interval and summarize it and go to the limit. So basically it's the same thing. Now in 3 dimensions, if the curve is not flat, if it's in a space, let's say in a 3-dimensional space, I can't even imagine how I can draw it, because there is no 4th dimension for the value of the function. But we still consider it algebraically, and that's exactly what I'm going to do to define a path or a line integral. It's called path because the curve is in physics, it's in most cases it's a path of movement of something. So the whole thing actually derived from physics. I mean, physics initiated this type of integral. Well, in as much as the regular integrals were really influenced by physics problems. So in any case, so we consider just as an example that you have a curve in, let's say, three-dimensional space, and I would like to introduce a concept of a path integral, basically to define it. How can I define it? Well, on the two-dimensional curve and using the value of the function at the third dimension, you can actually say something about the area of this little, very narrow, almost rectangle. In multi-dimensional case, like in three-dimensional case, it's not really easy to imagine what exactly happening. So basically we resort to algebra in this particular case. And the first thing that we should do, we should really find how can we define a curve in n-dimensional space. What is a curve? Again, from the geometrical standpoint, we can imagine what curve actually is. But since we would like actually to use some instruments of algebra or calculus, we have to really define it like more mathematically and less intuitively. And this is actually a very easy thing to do. Any curve can be very easily defined using some kind of a parameter. So let's assume that we are talking about three-dimensional curve. What does it mean that we have a three-dimensional curve? Well, it means that we have three functions S. Each one depends on some parameter S. So now S actually is a real number in some interval from 0 to S. Now, if we imagine that this curve goes from point A to point B, it means that x of 0, y of 0, z of 0, this point is A, and point B would be when our parameter has the maximum value. So these are 2 points. Now these functions of this parameter must be smooth, which means we don't really have jumps in values. So as S is moving from 0 to capital S, our points are not jumping all over, they are really go along a smooth curve. If S is changing a little bit, my x, y, and z also change a little bit. It means they are differentiable, basically. So if this is true, then this particular thing can be a description of the curve. Okay. Now, if in a regular integral we had an interval from a to b, and for each point we had the value of the function, here we also can have that for each point from a to b, and each point is basically calculated as some kind of a y at s, z at s. This is the point when this s is somewhere in between. We have some value of the function, which means that's what it is. So function of a point becomes actually a function of one single parameter. Now, if this is a curve, let's call it gamma. This is a curve. So I basically define, this is a definition of integral of function f at, well, I don't know, from some kind of a point, if you wish, but I can put x of just x, y, z, g gamma I use d gamma without actually, this is all kind of a symbolic thing. I'm not defining d gamma. And here I will put AB, which means I'm integrating this scalar function, scalar because just a single value, on each point x, y, z along the curve gamma, which is from point A to point B. I'm just defining it as a regular integral from 0 to s function f of x of s, y of s, z of s, ds. This is a definition. I mean, nothing to it. And now this is the regular integral from s is equal to 0 to s is equal to capital S. Function f, it's really a function of a point, but each point depends on single parameter s, which makes function f depending on single parameter s. So this is some kind of a function f of s, if you wish, this thing. And gs, and this is the regular integral. So this is how we have basically reduced a concept of integral along the path integral or line integral or curvilinear integral sometimes is used. So this path integral is basically defined as reduce the definition to definition of the regular interval, and there is no mystery in it. So as long as we have defined a curve using these three functions for three-dimensional case or n functions for n-dimensional case, doesn't really matter, we can define integral, path integral along this particular curve, along this particular path. We can define it as parameterized thing. Nothing to it. Now, what can be an example? Well, example is some simple. For example, you would like to measure average barometric pressure as you are going along some mountainous area. Mountainous area means you go up and down, left, right, etc. So you are going along certain paths and you would like to average the barometric pressure. How to do it? Well, you should really measure your barometric pressure at each point. Now, what can be a parameter? Parameter can be, for example, the length from the beginning of this path. So in the beginning it's 0, at the end it's basically the total length of the path in meters or whatever measure you would like to use. And on each point, which means for each value of s, you measure barometric pressure. So basically you are going on each point along your path, and each point has three coordinates because it's somewhere in space, in three-dimensional space. However, it's all reduced to a single integral. So you can say that basically then you can take this integral, since at each point you have a parameter s, which is the length you have covered from the beginning. So at each point you have basically this function x, y, and z, and you can say that the barometric pressure at point x, y, z is such and such. But all x, y, and z are functions of s, so that's how you can integrate it and then divide it by the total length of the path, and you will get an average. So that's basically an example. Now, this is one type of path integrals. This is the path integrals of a scalar function. Now, scalar because we have only one single value of the function for each point along the path. So the path is multidimensional. Let's say it's a mountainous path somewhere, and the barometric pressure is your single value function. Now, in physics, there is another very important concept, which needs vectors. We are talking about work. So let me go back to definition path integrals, but in this case for vectors, not for scalar functions, but for vector functions. This is a little bit more complex. Let me start from the very, very simple thing. If you have, let's say, a straight road, and you have some kind of an object, and it moves, and let's say there is a friction or something else, but you have a fixed function f which goes along this direction, and you cover the length, let's say d. So what is the work which is done by this force f or vector f along this particular road during the distance d? Well, we know this is just a product of these guys. Okay? Now, this is a simple thing. Now, what if f is variable? So it's still directed along the path. Let's say it's car engine. Car goes straight, but the road is different, and therefore the engine has to move, has to exert different forces to move. There are some more resistance, less resistance, whatever it is. But anyway, engine goes straight, the car goes straight, but the engine exerts force depending on certain conditions. So let's say x is the length covered from the beginning, and for each x, based on, let's say, friction of the road, f is different. But still, you have to cover the distance, let's say, from 0 to z, for example. Now, how to calculate the work in this particular case? Well, again, you divided the whole area by small pieces. Now, this is delta x, I, as usual. This is a regular integration. And you have to integral from 0 to maximum, let's say it's d, f of x, dx. So if you know f of x, which means you know the force which is supposed to be to overcome, let's say, the resistance, the friction or whatever it is, that's your regular integral. Okay, now let's complicate the picture. Now, what happens if f is not the, let's say, force which car actually moves you? Let's say we are talking about the sailboat, and the sailboat goes this way, but the wind goes this way. Now, if you have an angle between the this is direction and this is the force, how to calculate the work in this particular case? Well, if you remember physics, you just have to project f vector of the force onto vector of direction and multiply this by corresponding amount of road which you have covered. So what is this? This is absolute value of the vector times, let's say you have covered a very small let's call it delta r vector of the path. So you calculate it times this times cosine of angle phi. Right? This is the cosine of this, which is actually a scalar product of vectors, dot product. That product is actually calculated as length of one, length another, and the cosine of angle between them. So this is the definition of the work in case force F is not directed along this straight road. Okay, let's complicate it even more. Let's say our road is not straight, but a curve. And this is how I would like to approach integral of vector function along a path. So path integral of vector function. So before we were talking about path integral or line integral of scalar function. Now I'm talking about path integral of vector function. Why? Because it's very important for physics. Okay, so how do we define it? Well, basically I have already done the whole thing here. Obviously, if you have some kind of a line, and how can line in multiple dimensions be defined? Well, as I was saying before, x of some parameter s, y parameter s, z parameter s for three-dimensional case. Or we can say this is vector r of parameter s, right? Because 3 points define the vector. Or n points in n-dimensional case, right? Fine. So how do we calculate this particular path integral? So this is the key. So you basically have to multiply as a scalar product vector f and infinitesimal piece of the curve, obviously. Okay, infinitesimal piece of curve, we can use it dr, let's say. Now, what is dr? Well, it's this is a vector, right? Vector has three components. Three components are dx, dy, and dz in three-dimensional case. I'm not talking about n-dimensional, three-dimensional is enough actually, right? So this is an infinitesimal increment along the curve, where r is the vector r, which depends on certain parameter, and obviously these things also depends on the same parameter. Okay, now f is a vector. Now f also depends on three, in this particular three arguments, x, y, and z. Now, but this is a vector, which means it has three components: fx, which depends on x, y, z, fy, and fz. Each one of them depends on all these x, y, and z. And x, y, and z, in their turn, this is the coordinate along the curve, along this path. They all depend again on parameter s. So what should I do to calculate the work? Well, this is the key. So the whole integral of vector f times dr along some kind of a path from A to B. What is this? Well, if this is a scalar product. This is a scalar product. Do you remember how scalar product actually is supposed to be calculated in coordinate fashion? It's x coordinate times x coordinates plus y times y plus z times z. So the whole thing actually can be divided in from 0 to s. The s is the maximum parameter, which corresponds to the end point. 0 is the beginning, corresponds to the beginning of the point. And now I just have to really do very, very simple thing. F of x of s, y of s, z of s times dx. So the first coordinate times the first coordinate plus, and x is also depends on s, right? Plus second component fy times dy plus fz times dz. And all of them are functions of x, y, and z, which in turn are functions of s. All smooth functions. And the whole thing is, now, this is just a function of s, and obviously dx can be changed into dx by ds times ds, and now we have ds which can actually be taken out completely. So it would be x component of vector function times basically velocity along the x component, and then velocity along y, etc. So altogether, you can actually say that this is a scalar product of the force times the velocity. And that's where we are merging with physics in this particular case. So this is how you calculate the work of, let's say, the wind, which goes in one direction, along the path of the sailboat, which goes to a slightly different direction, not necessarily straight along wherever the wind is blowing. No, we are going somewhere else. But we are using the sail to position it properly so our movement would be wherever we want. And so we are moving along certain paths, and that's how we can calculate the work of the wind. So in any case, the path integral of either scalar functions or vector functions, in all these cases we finally reduce them to a regular integral by regular real parameter from 0 to whatever the value is. So this is all about definition of the path integral, and the path integral in this case is defined using all these concepts which basically lead you to regular definite integral of real functions on real arguments. Well, that's it. Now, I suggest you to go to notes for this lecture, because they basically describe the same thing, but maybe in some other words, maybe better words than I'm doing right now. So you go to unizor.com, you go to Math4Teens course. Now this is continuation, I think it's called Integrals Part 2, and that's where you will find the path integrals. That's it. Thank you very much, and good luck.